Okay, let's get started. Sorry about the thing.
I'm glad we sorted it out.
Okay, hello everybody. My name is Qiuyi, and I'm currently doing my postdoc at Alibaba Cloud with my primary interest in AI for genomics. Today, I would like to share with my latest work named Generative, a long context generative genomic foundation model. Okay, just to say, before we get started, just to say that we're almost midnight here in meeting, and I probably just lost 50% of my mind. So if you find me losing concentration during the talk, please forgive me, and I'll try my best not to, okay? Let's get started. So first of all, I decided to start with the comparison with Evil 2. I mean, this was supposed to be on the 20th page also, but I decided to move it up to the front because I guess this might be of your greatest interest, okay, as it's probably the most famous genomic foundation model in recent days. I mean, for obvious reasons, we couldn't afford to fine-tune Evil 2 as it's too big. Therefore, we only compared two zero-shot tasks, namely the variance defect prediction and the next k-mer prediction, which we will detail later. In short, Evil 2 is better, which I guess shouldn't be too surprising. Evil 2 with 40 billion parameters performs best on both tasks. But we're not bad either, as Generator 3B, as you can see, is almost in parallel with Evil 2 7B. Moreover, it was mentioning that Generator 3B is more than 100 times cheaper and 100 times faster than Evil 2. And very, very, very importantly, we support a much broader range of GPUs so that you don't have to keep chasing the latest GPU in order to use your service. Okay, that's a quick comparison with Evil 2 just for your interest. And we definitely shouldn't spend too much time on this comparison. And now let's just officially get started. Okay, we start by having a brief review of large language models for biological sequences. And I probably don't even need to mention the protein language models, such as AlphaFold, ESM, and Protein, which excel at mapping the amino acid sequences to protein structures, have significantly transformed the proteomic analysis in recent years. I mean, the fundamental idea of the genomic language model is largely similar. So we basically aim to leverage the large language model to decode the DNA sequence, which is generally considered to be more complex, but having more abundant information as well. Okay, now you may have one question in mind. Isn't the genomic language model trivial? So basically, you can just replicate whatever has been done in the protein language model, but with DNA data. Well, I mean, that's indeed what has been done at the early stages. But soon, people have realized that modeling DNA sequences is more complicated than that, mainly due to the fact that, well, the DNA sequences, or a comprehensive DNA sequences, can easily extend to tens of thousands of nucleotides. The protein sequences, on the other hand, mainly measure in hundreds of amino acids and is less noisy, which makes them perfectly prepared for the transformer architecture as have been seen in the large language models. This also explains why the usable genomic language model comes so late, while the usable protein language models comes much earlier. Here we have the table of the development of genomic language models. The earliest development can be traced back to DNABird in 2020. Over the last 5 years, we have witnessed numerous attempts for improving the genomic language models. I call this the game of combinatorics, where people from all over the world invested their time on testing different combinations of model configurations. I mean, this game still hasn't reached the convergence yet, at least in my mind, but it becomes rather obvious that these models have become larger and larger. like 7B, 4B, 3B, 40B. Well, it start from a couple of, well, tens of millions parameters. And the contexts are getting longer as well. And the pre-training task seems to transform from the mask language modeling, as in the BERT model, to next token prediction, as in the GPT model. Well, this was one of our old slides. Well, I mean, apparently this statement no longer holds true anymore, given UO2. But never mind. I mean, I just keep it here for showing that, well, I mean, the story could have been completely different. We were quite ambitious 2 weeks ago or 3 weeks ago. But never mind. We have figured a new way out, as we are still the most cost-effective in the field. As I mentioned earlier, we are like 100 times or probably even 200 times cheaper than Evo2, where we're having comparable performance. But I mean, we are cost-effective not because we're lucky, but because we were prudent and we tried very hard. We spent more than 200,000 GPU hours testing the best pre-training paradigms for DNA language models. And very importantly, or very interestingly, we found many, many observations to be counterintuitive. Alongside the generator model itself, this pre-training experience is what we evaluated as the most valuable. And it's also what I would like to share, with you today. So we first start with data processing. For training the generator model, we sourced all DNA sequences in the eukaryotic domain from the RefSeq database. We tested 2 different pre-training paradigms. The first one is named gene sequence training, where the model is trained solely on the annotated functional DNA sequences. We must note here that these functional DNA segments do not only refer to the coding regions, but also include the RNA regions and a broad variety of regulatory elements, such as promoter, enhancer, untranslated regions, introns, and etc. Okay? In contrast, the all-sequence training paradigm refers to the conventional pre-training paradigm where all sequence data are used for training. Okay, as you can see from, I don't know if you can see my mouse, but never mind.
Yes, we can.
Okay, thanks so much. According to the pre-training loss, okay, this all-sequence training paradigm has a lower pre-training loss. However, I mean, this is the first place where things start to get counterintuitive, because we have also tested or even evaluated the model performance on a broad class of genomic tasks. What I showed up here is the revised NT tasks and the original NT task, but we have also tested many others. You can find them in my paper, okay? But just to say that we're tested tens of different benchmark tasks, where we find that this gene sequence training paradigm displays or significantly or consistently outperforms, despite it have a higher pre-training loss. Okay, we found this to be counterintuitive. And if I have to give an explanation for this, I would say that DNA is not a concise language, but rather filled with randomness and redundancy. Okay, if we're allowed to make a bold assumption that at the origin of life, the DNA sequence was almost entirely random, then over billions of years of evolution, random mutations or other evolutionary events have given rise to a limited number of biologically functional segments. And these segments represent the semantics of DNA. Well, in contrast, the vast majority of the non-gene regions largely consist of segments that have not yet acquired the function. Okay, this region often include highly repetitive and simple segments, therefore contributing to a lower pre-training loss. Okay, that's just my assumption. Okay, just like I said, if I have to give an explanation for this counterintuitive results. But as a result, the generator model follows the gene sequence training paradigm, focusing only on the semantically rich regions. Sorry. Now, we proceed to the tokenization method, which convert the DNA sequence into a sequence of tokens, which is suitable for training large language models. Overall, I should say that a good tokenizer should strike a balance between sequence resolution and context coverage. And to this end, we tested 3 different tokenizers. As the most fundamental tokenizer, the single nucleotide tokenizer offers the finest granularity, okay, yes, yet covers the shortest context. The K-mer tokenizer, on the other hand, treats all possible combinations of K nucleotides as tokens. It scales the context coverage by K at the cost of losing sequence resolution. The BPE tokenizer, as you might be familiar with, works by aggregating the most frequent subwords. As the best practice in natural language processing, we initially anticipated that BPE might be the best tokenizer for DNA sequence as well. And we evaluate the performance of these different tokenizers using a task we called next K-mer prediction. This next K-mer prediction task involves inputting a sequence segment into the model and having it to predict the next K base pairs. Okay, this predicted sequence is then compared to the reference sequence to assess accuracy. And we believe that the sequence recovery ability is fundamental to the task of sequence design. And surprisingly, as I said, things start to get counterintuitive from this point. Surprisingly, according to our evaluations, the BPE tokenizer significantly falls behind. As you can see from here, the BPE's tokenizer are dashed in this next K-mer prediction evaluation graph. Okay, but the K-mer tokenizer, or specifically the 6-mer tokenizer, emerged as the most effective. Before I tell you the reason, I would like to show you one last experimental study about the model architecture. Okay, as discussed earlier, a key challenge in training the genomic language model is long context pre-training, because DNA sequence is very long. And the training efficiency of the transformer model will drop sharply as context extends. And on the other hand, okay, there are some alternative model architectures, such as Mamba or Hyena, recognized for their capacity in handling long context data. And indeed, there are many approaches, including EVIL, seek to use these more streamlined architectures for more efficient long context training. To this end, we trained a Mamba model and tested on next K-mer prediction. Okay, this Mamba model was represented by this dashed and dot line, whatever you got here. Okay, but I mean, according to our experience, although the Mamba model demonstrates superior training efficiency, it does not demonstrate equivalent sequence understanding ability. Okay, I mean, I guess the intuition behind it is relatively straightforward. Say, if you read a book for 30 hours, you're supposed to have a better understanding than reading it for 3 hours. That is basically the idea behind it, I guess. Okay, we call it there's no free lunch. You cannot spend less time and do a better learning. Okay, finally, we made to the pre-training phase. And I will also give one possible explanation, as I promised, about why BPE works poorly in DNA language models. I mean, the pre-training of generator is straightforward. Basically, just a 6-mer tokenizer plus next token prediction and trained on gene sequence only. Okay? And indeed, well, there are 1 or 2 nasty guys have challenged me on the internet, saying that, well, I mean, your model is cheap. I don't see any innovation in it. And I have to say, well, I mean, mate, you kind of get a point. I mean, our model is cheap. And the key innovation is that we let things stay as simple as it should be, which is very important. Okay, sorry, I'm not sure if you're laughing or not. But anyhow, let's stop joking and have a look at the difference between K-mer tokenizer and BPE tokenizer. In the next token prediction per training, the model is asked to predict the next token, as if I said nothing. In the context of K-mer tokenizer, all tokens. What? I'm sorry, I saw somebody post a comment, but never mind. I couldn't see it now. Okay, I'm sharing screen. Never mind. In the context of K-mer tokenizer, all tokens are mutually exclusive. So basically, the task of next K-mer prediction or next token prediction is learning to predict the unique correct answers. Well, on the other hand, in the BPE tokenizer, these tokens often have nested relationships, and the model not only need to predict the following, not only need to learn to predict the following context, but also need to decide how many base pairs to decide to predict. Sorry, and this unnecessarily complicates the training process. And I call this the dilemma of BPE, which is the problem where you have unique label with multiple correct answers. And this indeed also reveals a central difference between DNA and human language. As we all know, BPE works well in the human language, but I guess that's mainly because human language has clear lexical boundaries, such as Apple. These 5 letters always stick together to have a specific meaning, okay? But DNA does not. Sorry, just a little time. In the following time, I'll quickly go through a few examples of model application. Overall, as a generative model, the generator can undertake both protein design and DNA design tasks. And for protein design, we fine-tuned the generator model using the protein coding DNA sequences for the cytochrome and histone family. These generated protein coding sequences are then translated into protein sequences using a codon table. And we compare these generated protein samples with natural samples across a variety of summary statistics. Specifically in figure A, we demonstrate that the generated sequences have stable codon structures and can be smoothly translated. And the length of these translated sequences closely resemble the distribution of the natural family. Okay? In figure B, we tested whether the protein language model can recognize the generated sequences. And the answer is yes, as we observed that the perplexity distribution closely resembled the natural family as well. And in figure C, we validated the foldability of the translated sequences using AlphaFold 3 and FoldSeq. And we find that the generated samples primarily reside in the high confidence region. Okay, the high confidence region referring to the region on the top right corner. Okay, where you have a relatively high TM score that is greater than 0.8, and you have an average PLDDT. Well, PLDDT refers to the confidence of AlphaFold 3 prediction. Okay, greater than 80 or so. Okay, and in figure D, we give 2 folded structures of the generated samples. And these samples display structural congruence with the natural samples despite having low sequence identity. Okay, this low sequence identity positively suggests that the generator model is not merely replicating existing sequences, but have learned the underlying principles to design new protein molecules with similar structures. Because that's for protein design. Actually, we have repeated this experiment for the histone family as well, and the conclusions remain largely the same, just for showing that the model's capability for protein design can be generalized to many other families. Okay, here we go. This is the most important application in my mind, okay? Because we can do enhancer design, or more generally, the design of any meaningful DNA sequences. And this sequence design task is GLM, like for genomic language model, exclusive, okay? Utilizing the deep star enhancer activity data, we fine-tune the generator model to predict the enhancer activity. Basically, the enhancer activity means how good or how bad it can boost up the gene expression. Okay, and this predictor model surpassed the deep star and NT multi-species, establishing itself as the current SOTA promoter activity predictor. Okay, and to optimize, or for the sequence design, to optimize the enhancer activity, we also developed a prompt responsive fine-tuning approach, which allows us to use prompts such as high and low to generate enhancer sequences with desired activity profiles. So basically, we just say, give me a high activity enhancer, and the model will just start writing a DNA sequence. And if you kind of predict it, or if you kind of evaluate it, you will just be able to find that the average, okay, the average or the expected activity of this group tends to be significantly higher than the natural family or than the low activity group. Okay. Well, recently we have just submitted 100 samples to the wet lab for further validation, but we're still waiting for the final result to come out. So unfortunately, we can't give you a solid justification of our designed enhancer sequences does actually work. Okay, the figure or the density plot that you can see from here, it's just we use the activity predictor to predict the activity of these generated samples. And you can still see that if you believe the enhancer activity predictor is right, then you will just still be able to see that this low activity group categories and high activity category and the natural samples exhibit significant differentiation between each other. Okay, and we should also mention that all the reported results in this talk, not just on this page, okay, in this whole talk, are derived using the smaller version of generator, which is generator with 1.2 billion parameters. The reason behind it is just we hadn't prepared to release generator 3B until EVO2 came out. But it also positively suggests that you might not even need a huge model to do these aforementioned tasks for protein design, for example, or for enhancer design. Okay. That's basically all I have for the generator model, but I would like to say a little bit about our ongoing work named Generator, which hopefully will be released very soon. Okay, Generator is a mask language model with 500 million parameters, just the same as nucleotide transformer version 2, NTv2, okay? It is by itself a good GLM, we have tested the performance of generator on this benchmark tasks. And you will just be able to see that it's almost in parallel with the smaller version of generator and consistently outperform the others. Okay? But more importantly, well, I mean, although generator does not have generative ability, okay? It's a MLM, it's a BERT model, okay? But it's a good annotator. Our evaluation results demonstrate that it beats the dominating gene annotation method, Augustus, showcasing its potential to become the new annotation standard. I mean, we're very excited to see the result, but of course, it's a very, very bold statement. Therefore, we just want to be more cautious, and we have to test more thoroughly before the official release. Okay. Okay, that's basically all for today. Lastly, I just want to say many thanks to my teammates, especially to my intern student, Wei Wu. I just want to say you really did a brilliant job, and we wouldn't have made it here without you. Okay, you are a really good student, and we made a really good team. And that's all for today. I probably go too quickly, but we can have more time for questions as well. And thanks for listening. And last but not least, feel free to subscribe us and stay tuned for more updates. Thanks.
Wonderful. I would like to thank you for that wonderful presentation. Thank you very much. Thank you for the little tidbits of what's to come, Generative. If you ever need a forum to present it in, you can always reach out. And the multi-omics reading group will have a place for you to show that. Mm-hmm. So with that, I would like to open up the floor for any questions. Any questions in the chat? We have a question by Jack Stanley. Jack, please go ahead.
Hi, thanks. That was a very interesting talk. I was just wondering about, so this is a question about, I guess, all these genome foundation models, these DNA foundation models. How do you deal with sort of overfitting, I guess, to the training set? Because it seems like, although you have lots of different species, am I correct that you only have like one human reference genome that you're using, or are you using multiple references? Like, how would it work if you want to do some like out of sample evaluation on non-reference sequences?
Okay, that was a wonderful question. I mean, this is the most, well, I mean, I could say this is actually the most interesting part about DNA language models or DNA foundation models, because, I mean, we're not afraid of overfitting at all. Because let's just say, taking your statement before, like, it doesn't really matter if you're using one human reference genome or you're using 10 different human reference genomes, because they are more than 99.9% identical. So this is the idea of, or this is a very, very important idea behind the genomic model or genomic foundation model, which is like, if only you can memorize every single DNA or every single genome, you would just be able to predict them correctly, because there is no you cannot simply just come up with a species or a animal or something that has not been sequenced before, or that has completely different DNA structure or something. So basically, we are having a world model that every single sample shared more or less the same information.
Yeah, I think that makes sense. But I mean, you're also concerned like with the small differences, right? Because like, for example, if you do ClinVar,
okay, I see what you mean.
Are you not essentially just comparing like to the reference, and then does that make sense? Like the reference, you're basically just not necessarily looking at the disease information. You're more looking at the difference to the reference instead of.
That's indeed correct. I mean, as you can see from here, we did do the ClinVar or the variance effect prediction, and apparently both generator and EVO2 did a pretty good job. I mean, I gotta say, or I gotta admit that this was beyond my expectation. I didn't expect it to be so good, but somehow, I mean, well, I guess this has something to do with the law of large numbers. Say, for example, you have trained like 1,000 different genomes, and the majority of these genomes would have high fitness. Okay, because I mean, most of the samples drawn at random will be healthy or would be fitted. So the law of large number would tell the model, well, this kind of nucleotide or this kind of variant show up more frequently, so it's more likely to be fit. And those nucleotides which appears less frequently are more likely to be something that will cause your disease or something.
Yeah, that makes sense. I think we'll have to wait and see until some applications are built on top of these models to see how useful they are in all of these settings. But I think it's very, very interesting. So thank you. Yeah.
Great. So we have a question in the chat. I'll read it out loud. Unless Dylan, you want to go for it, or are you in the silent section?
Oh, I got this question. Say, do you think that supervised pre-training tasks will be useful, similar to Informer for the genome models? Perhaps these tasks could mirror the NT evaluation tasks. Well, a good question again. But I am not keen to the supervised pre-training. I'm rather lean towards unsupervised pre-training with supervised fine-tuning, because, well, we named the generator as a generative gene foundation model. The reason that we named foundation model means that we want it to be as general as possible. Basically, it just says that we want to keep every single possibility for the generator model to do all kinds of downstream tasks. But if you're going to have a supervised pre-training, that will probably drive the model towards certain directions, which will do well, which wouldn't be very, very good for the generalizability for the model for other kinds of downstream tasks. Well, that's just my think. But if you're going to have an expert model, for example, say, I just want to do this. For example, I just want to do variant effect prediction. Then I just train a large language model specifically for variant effect prediction. That's gonna be good as well. And indeed, I could recall a work called GPN MSA or something. That's pretty much the same. Following the idea. Okay.
Great. Any more questions? There's a question in the chat about region selection.
Okay. Wait. How am I supposed to? So could you please uncover more details on how you select gene regions during pre-training? Well, that is our killing techniques. And we're apparently, yes, we will, as I promised, we will release these training data at some stage. But we're going through, I mean, you know, I work in a large company, and there are lots of rules that you need to follow in order to, you know, to uncover the data correctly or something. We're still going through those tedious procedures, but I shall be able to make it in the end. Okay, I cannot give you a sharp time about, so I'm going to release it the week after next week, but we'll definitely release it soon, as soon as I can. Okay, and if you ask me how we managed to do that, well, that was tedious, and that was not easy at all. Basically, you just download everything in RefSeq database, and you just subtract the annotation and just compare the annotation with the raw sequences and just subtract it out. Okay, we spent a lot of time on it, and we believe that this dataset is very useful, it is very valuable, and the good news is we will give it to you later on. Okay.
There's one more question in the chat. It says, it's a follow-up to the last question, but it basically says, you mentioned that the gene coding pre-training strategy outperformed the all pre-training strategy. Do you envisage other annotation-guided pre-training tests?
Yes, we did. And that is indeed what astonished us. One of the tasks that astonished us the most. Okay, we like you may have been aware of, like we have this Generative model for gene annotation as well. And this Generative model is also trained using gene sequence training paradigm as well. I mean, we have tested both training paradigms, and even if this is the case, when we are doing gene annotation, the gene sequence training paradigm would still outperform. I mean, I have an hypothesis, or I have a assumption for this as well. So basically, if you're training using or solely on this gene sequences, so basically you will recognize, let's say, basically when you're doing this annotation job, okay, you will recognize where are the gene regions, because you will only be able to recognize the gene regions. While the non-gene regions to you or to the model itself will just looks like random noises. So basically, you're just doing, well, we're trying to find the meaningful sequences in rubbish or something like that.
So I'd like to start a little discussion on that final point. You draw parallel of non-coding regions, or everything that's not in the gene selected strategy, basically the DNA junk, as some people would call it, as noise, right? But
Yep.
sometimes, like, not having this noise in the model will help you out training a better model that's more accurate at predicting, or at least here you show it very clearly how the gene coding variant does actually better in predictions.
Mm-hmm.
To everybody who's trying to build foundation models nowadays, what are your thoughts, or what would be your advice on how to deal with non-coding regions? What would you do to these? Would you just prune them? Would you maybe try and learn the noising patterns? Just something to this end, right?
Okay, yes. I mean, that's a serious question that I probably shouldn't give you a very, very specific answer, because it will be too risky. So basically, from our experience, I mean, we truly didn't find those non-gene regions to be helpful at all. But I mean, thinking of it from another perspective, we're trying to solve, or the generator as the genomic foundation model that we train are supposed to solve 90% of the question perfectly, or we're supposed to be able to solve 90% of the question with 90% accuracy. But the remaining 10%, which I referred to the non-gene regions, remain undiscovered. Well, alternatively, if you're gonna do the whole sequence training, or if you're gonna do the all sequence training, you're gonna include those non-gene regions for training the large language models. You might be able to have some understanding about those dark matters, like people would say. But you will, at the cost, or you will have to sacrifice the model performance on those gene regions as well. So we made this trade-off, or we decide to give up non-gene regions, but we would like to reserve the best performance on gene sequences or on gene segments. But I couldn't say, or I shouldn't say, there's absolutely no value with non-gene regions.
Very insightful. Thank you very much. We have another question in the chat.
Could you tell more about the accuracy of different tokenizers? If using K-mer tokenizers, how should the model be? Oh, okay. That requires a little bit of trick. Well, actually, we have this open source on GitHub. If you're gonna check out the codes by yourself, you will just be able to figure it out. But never mind. So basically, if I want to do, say, how am I supposed to say this? We have a K-mer tokenizer, but we can find the probability, say, we can find the probability for any single nucleotides by calculating the cumulative distribution. Basically, if I want to see what is the probability that the first nucleotide in a K-mer token is A, all I need to do is to, first of all, you're going to output the logits for every single token, like every single K-mer token, okay? And you're going to sum up the probabilities or the logits where the first letter of the token is A, okay? And by summing them up, you will just be able to find, or you will just be able to add up a marginal distribution where the first nucleotide in your token is equal to A. And that's basically how we managed to do a single nucleotide variant effect prediction.
Wonderful. Are there any more questions in the chat? Maybe? Anybody want to raise their hand? If there's no more questions, let's take a minute to thank our speaker again. Thank you very much. And well, if that's everything on everybody's end, that finalizes the recording. Thank you very much.
Thank you. Thank you, everybody. Bye-bye.